Okay. Okay, hi. So my name is Janus Troelsen, and well, I'm presenting a data structure. It's like it's a hash-based, right, accumulator. So I tried to describe what it is in the abstract, but basically, an accumulator is something that stores elements, and you can then verify that they exist inside. So you can compare it to a set, right? You can if you have a set, you can say we have these elements, and just the fact that you have the set is then a proof that every element is inside the set, right? But the problem is it requires the storage of all the elements. So so I'm going to present here like an accumulator that allows you to prove that elements are inside without actually requiring all that storage for all the elements. And yeah, and well, it's the only application that I know is in Bitcoin, but I want to present it in a way so that it's not only for Bitcoin. So let's see if I can do that. And but you know, like all the primitives are based on, it's just based on hashing and, you know, proving membership and stuff like that. So that's why I'm thinking like this should be usable for other things. But since I only have the Bitcoin reference for usage, I will then try to, you know, I will give examples with Bitcoin. And because I have a lot of time, I think everybody should just, you know, raise a hand if they have a question, and then I will explain if I can. But well, I only have this one use case, so you know, every example will just be like, you know, if you need a concrete example, then I will say, okay, this is how it will be if it was with Bitcoin. Okay. So here's the agenda, and it's basically just a run through the algorithm, and then, you know, I have some questions that I haven't even resolved, and yeah, and then I will talk about them. So basically, I will present all the stuff I know, and then I will have some questions, and then maybe it can be like a discussion. Well, let's see. So the problem in Bitcoin is that all the Bitcoin that are not spent, right? They are called the unspent Bitcoins. They are inferred from the whole blockchain, right? So you have transactions, and each transaction goes into a block, and each transaction will be making, usually it will be making an unspent transaction output, right? This means it's a Bitcoin that could be spent if you have the right program, but it hasn't been spent yet. And this is actually like, it's the most important. If you're a user of Bitcoin, you want to know that, right? You just want to know, has my Bitcoin been spent or has it not been spent? So, and this set is then constructed out of the transactions, right? You take the first block, you have some genesis outputs, right? As they are called, like the first outputs. Each block makes new outputs, but it's also spending previous outputs. So that means you can't just, like, if you have the whole blockchain and you haven't processed anything, you have to go through the whole thing to see what was spent and where was it spent to and all that stuff. So that means this thing that I'm talking about, the 4 gigabyte set of unspent Bitcoin, it's like it's kind of large, right, for a phone, and it's super hard to generate, because you need to process like 300 gigabytes of data just to regenerate it. So the thesis of like the proposal of Utreexo is that you can, when you give somebody a Bitcoin, you can prove that it was not spent, because we now store all those all those unspent outputs in the accumulator, and we can prove that things are in there and not. So any Bitcoin user that is like up to date with the chain, right? He's downloading a block, he's applying the changes to his local set. He will then be able to receive any proof, and it will be specific to his state. And the advantage is that he doesn't need those 4 gigabytes, right? Because he doesn't store the actual set. He just stores a commitment to everything that's inside the set, and that's fine, right? Because we just want to know that it's definitely not made up Bitcoins. When you receive some Bitcoins, you want to know these are not spent at this latest block, right? But the accumulator does need to be updated. So this is the big question, and this is like what the solution is about. So we put all the, we have all the transaction, the outputs that are unspent bitcoins. We have them as leaves in a tree. Okay, and it's a perfect tree. That means every node has 2 children, and if it doesn't have 2 children, it's because it's at the bottom. So that means it's not an unbalanced tree, and like every path goes down to the same length, right? So you will see some pictures later, and you will understand that. And it's a hashed as a Merkle tree, right? So that every node is hashing its children, and I will show you this too now. And as I talked about, you can prove that an element exists just by providing the path, right? Down the tree, you provide some hashes down the tree, and then because the top node is committing to everything in the tree, and hashes are made in a way so that that's not supposed to be 2 different sets of data that, I mean, you cannot have 2 different sets of data that hash to the same thing, right? That's an assumption of the hash. Even though it's not actually true, we can assume it to be true. And this is why we can have this space saving, because, you know, just this exists. Okay, so I will not actually show what a Bitcoin output looks like, because it doesn't matter, because we're talking about set memberships, right? So I will only talk about this tree and how to manipulate it. And then you have to know that every leaf in that tree would have some Bitcoin script associated with it, and it will be like, you know, this user with this public key can spend this, right? That's what Bitcoin outputs say. They say like, I restrict myself to being spent by somebody who can sign with this key. So yeah, and okay, so here's our example tree. So as you can see, it's perfect, right? And all the nodes from 0 to 15, they are the leaves. So they would be outputs, and then 30, the top, would be the it would be the commitment to all of those nodes. And each node, like 16, will be a hash of 0 and 1, right? And if we want to prove that any node exists, we have to give all the sibling hashes. Like, so if we want to prove 4 exists, we'll give 5 and 18, 19, 25, 28, like going up the tree. So yeah, like this. If you have like some hash, that will commit to every other. Okay. So this is kind of what I hinted at earlier, that we're always changing the tree, because every block in Bitcoin will be changing that set, right? So how do we change the trees, right? We don't want to rehash everything, because that's a lot of data, and we can't rehash everything, because the point is that we don't store the whole tree. We can manipulate the tree, even though, because if we only touch things that are not, like if we're going down a path, right, and we only need data that's from a specific path, we actually don't need the other stuff, right? So that means we can manipulate the tree, we can shuffle things around, because we know, like, for example, that a sibling is committing to a subtree of this size. But if we don't touch anything, we don't need to know what that is. So so this is also like the second last bullet point is what I hinted at earlier. Like full blocks, they tell us all the data, right? But so we download the full block, and then we can manipulate that accumulator. And then you say, okay, if we need to download the full block, what's the point of all this, right? Then we could just download all of it and sync like a normal Bitcoin node does now. But the point is that a normal Bitcoin node nowadays works in a way where it actually needs to store that full set, because it's not smart about how to reason about the set. So the improvement here is like you have equivalent security because you trust your hashing, and you have more bandwidth usage, right? Because you need to pass proofs around. Like if I want to prove to somebody that a Bitcoin exists, I have to prove that it wasn't spent in that accumulator root, right? So this is something you don't have to do now, because now you just say, okay, here's my script, and Bitcoin node can just say like, okay, I see that there is an unspent output, you know, so I don't need to prove it because there's no data structure. There's just a set, right? How do you prove membership of a set. You just assume people have the set, right? Then you know that they know that it's not used. Okay. So okay. So now we will. This is an example of the committing that I showed, and here's like again you can see 27. I don't know if you can see the colors, but yeah, 27, 28, 11, 20. Those are like the auxiliary hashes, right? That we need to prove that 10 exists. Okay. So, and here's how it would be used if you actually were using Utreexo, right? You would need to, the receiver, you can see the last bullet point, needs to, even though they only have the tree roots, they can check that that the output exists. So when you receive coins, you will also receive a proof that your new output exists, and you know that you decided what this output was to look like, right? When you ask for Bitcoin, you ask for somebody to spend to an output that you decide. And then you can then prove that it exists, and then you can prove that even without losing security, right? But using a few gigabytes less of persistent storage. So let's see. Okay, so I'm going through the algorithm to do the deletion, because doing the addition is easy, but maybe I can talk about that later. So the deletion is like split up in these rules, and don't worry about the names, because the names are like, they are kind of, they just have to be some names, there's no names for all this, so we just invent some names. So so you can see here what they actually like correspond to. We identify some subtrees, we move the subtrees around, and and then there's two different kind of ways to swap subtrees, but I will show you how that works. And that's it. Then you swap the subtrees. You don't need to touch all the nodes, and you have updated your tree. You have deleted some nodes, and you can just add new. You can just add new outputs. Basically, you add new members to the set. No problem. That's easy. Okay. So this is the first step. So we're deleting the nodes 4 to 9, right? So they are in the middle of the tree, as you see, like in the middle of the leaves, right? Because only the bottom row is outputs. They are the set members, right? So we are saying these 6 outputs have been spent, and we want to remove them so that they cannot be proven to exist in the tree anymore. So there's this algorithm, extract twins. It's not a very large, I don't have the code here because I don't want to like go into the minor details, but it's like very simple. Everything's open source, and this is basically just pasted from my GHCI prompt. And you can see it takes a bunch of nodes, and then it gives some nodes on the upper row that would be the parents, right? So if you delete 4 to 9, you will be deleting 18, 19, 20. That's like the first row, what the first row shows of extract twins. Then you iterate up the tree, and then at the end, that. So that 20 and 25, and you can see that in the tree, like it's very easy. Like I've highlighted here with blue, you can see that 25 is like, identifying that subtree of stuff you want to delete, and 20 is identifying another subtree, right? So we have a couple of subtrees, and we can now use them in the next step. Okay, so there's this algorithm, make swaps, and it's taking those indexes of subtree roots, and then it is generating swaps. So you don't need to understand every parameter, but like for example the 14, the 22, 26. Let's not worry about that right now. But basically that's just actually the tree root, right? The 26 means that we are dealing with, when we deal with 25, we're also dealing with 26, because the 26 is tree root on that level, right? And all these algorithms work like level by level. So the point is, let's look at like the right row. You can see it results in 22, 20, 26, 25, and 14, 8, right? And what are those? Those are actually like the swaps we need to make to reorder the tree such that the nodes that we want to delete are deleted. So this is all derived from that list of deletion elements we wanted to get rid of. Okay, but there's an issue like, and this is like why there's not only swaps, there's also these collapses, and that's basically because some of the swaps you would do would get erased later. So, I mean, so the red arrow is what is called a collapse, right? We're trying to move the 14 to 8, and if you do that, then it will get moved to the end by the next one, right? By the 2220, because the 2220 thing would move 8 and 9 with 12 and 13. So there's another algorithm that takes care of this and looks at the swaps, looks at the collapses, and then turns the collapses into swaps so that we can just go up the tree, swap everything, and we are done. So this is what it does. It changes the 14.8 to 14.4, and then we can run the algorithm, like basically just going through the swaps we have, swapping them. So we have swapped one, right? You have seen now at where number 4 was, there's now number 14. So yeah. Because 14 was just its root in a one element tree. So it's very small, right? But it's still a tree, it's just one node. Okay, so we did the bottom row, we do the next row, we swap something. Now you can see like the 1213 in the bottom has been written, and the 89 is now at the end. Like it's the second last micro tree at the right. Okay, and here's another swap. And I've marked like the deleted nodes gray out, right? Because we have swapped them out to positions that would just be like, like stuff in your file system where you don't have a file, right? It's like it's still actually there because it's just one giant array, but you can imagine as if it doesn't matter what's in there anymore, right? So this is what's been happening. Like we've been swapping things to positions where we just decide this is not even part of the structure anymore, because all of this is embeddable into an array, right? To have fast performance and all that, and to implement it on memory and on file disk, and that's why, well, yeah. So it's convenient to talk about the indexes. But as you can see, what we wanted to do is we wanted to delete those nodes, right? And the 4 went all the way to the right, and the 5 through 9 went just before that, but it doesn't matter, right? Because those are deleted. So now we end up with one tree and then a second tree with just one node. But the point is, now we just need to rehash some of the data, right? Because we only swapped some of the trees. So we don't need to touch, for example, 16 or 24, all that left side, all that stuff. We don't need to touch that, right? But we still need to touch the root, for example, because we swapped things in there. But that's another algorithm, right? But it's not very complicated. Okay. So now I'm going to talk about like what are the extra tricks you can do, because I talk all the time I only talked about saving the roots, right? Because the roots commit to the whole tree. But you can do it smarter than that, because if you only store the roots, every time somebody tells you something is spent, you would need to say, okay, then, well, okay, every time somebody says this thing is in the tree, right? You would have to ask for the proof. But you could just, you can choose to save an arbitrary number of proof. It's just saving more nodes of that tree. Like you could say, I only store the root because the root commits to everything. But this is all about a trade-off between bandwidth and storage. So you could say, I just store the things that will be not spent for a long time. And maybe if you're using it in Bitcoin context and you're always syncing the same tree back up, then you will be syncing from somebody who knows when a Bitcoin will be spent. So you could say, this thing is going to be spent, in the next block. So you don't need to write it to disk, you can keep it in memory. So you can do all these optimizations. So and it's not breaking the trust model, right? Because it's all about optimization. It's just an optimization, and you can verify it at the end. You can lie to somebody for 99 years, but at last they will find out, at the very last moment, because they will see, oh, it doesn't add up. You didn't spend this thing you told me that you would spend. Then I need to download more proofs. Doesn't matter. Okay, so these are just the quotes, basically saying it in the formal way what I just described, that you could do basically you can, you know up front. So I will show this like how to just update the tree, and it's called, well, this is just what I've showed before actually. So, you have a node, you add another node, and you say, okay, I want to remember this node too, right? Okay, and then you add some more nodes, and you always commit to the top, right? The for has always been committed to. That's not even an option. But you say, okay, I save number 2, even though I might not care about it. I can still save it and say, because the server told me I will spend this soon, right? So don't throw away the proof that you made when you updated your tree. And we modify the tree more, and the client can just keep that proof, because the client knows where the leaf moves around. So the client also knows the client needs to recalculate that proof anyway, right? Because the proof is just nodes, it's just hashes. So so you can do these trade-offs. Okay, so yeah, we can trade storage for bandwidth. We can have Bitcoin running on devices that don't need like a lot of storage, but can have bandwidth instead, right? We only need to trust that hashes are trustworthy, and we don't delete stuff that we're not supposed to, stuff like that. So basically the algorithm I showed you, we need to trust that too, right? And then so my question was like, also, how can I even think about this in a functional way? So that's kind of a different topic, right? Because all these indexes, they are like so opaque, right? The index only means something if you know the height of the tree. So if you don't know the height of the tree, how can you say 14? It depends how high the tree is for that position to be somewhere, because we number the nodes from the bottom up. That's not how trees are made in functional programming languages usually, right? So the first line shows like a typical binary tree in Haskell, right? It's polymorphic over the type A, and it has 2 child nodes, or it can just be empty, right? But there's no difference between a node and its child. They have the same type. So there's no restriction even on this being a perfect tree, right? Which I would also like, because all my trees are perfect. So why don't I have a type to describe that? Okay, so then I read the Idris book, and I was thinking, dependent types, why not? So that's one way to solve this, and it would be interesting if there was another way. But you could say, okay, a node has to have children that has an index type, right? A type index type. So h minus 1. So the node of the children have a lower height than the parent, of course. And then you could actually transfer between this. Then you could calculate the old style index, and then I could write a new implementation that was functional, and I could still make it. I could test it against my old code, right? Working with these indexes, because I could then, if every node knows the relative positions of its children, well, then I can transfer between them, right? But I don't know actually how to do that, because I'm a bit worried about, like, can you really transfer in both directions, right? Can you transfer if I have a subtree, can I really know that it is, well, don't I know also need to know how many levels are above it, right? Well, in the Go tree, you can see when you hit the bottom just by, well, if the indexes are 1, all the other siblings are just XORed with 1, right? They are just like the bit is flipped, so it's really easy to, for example, make a sibling. It's also easy to make parents and children in the imperative tree, but, well, the Go tree, as I called it before. But in a functional tree, it doesn't really make sense to be able to go up and to go down at the same time, right? Because it wouldn't be an algebraic data type. How can you store? It would be recursive in both directions, right? For me, it doesn't really make sense. So what I need to do is I need to reason about, like, the indexes, I think. So that's like my question right now that I that's what I'm working on, and I don't really know how to solve it. But I wanted to say that, no, this is what I'm thinking of. Um, but yeah, it's well, the algorithm is not that big. I think it's hard to explain it because it's so much mutation. But yeah, come on. Yeah, yeah, okay. Okay, so the question was, do you know zippers, right? So there's, I don't know who came up with it first, but yeah, I've tried using that. The zippers, I tried using the one from Kemet, and they are like, they do allow you to go up and down, but they are really hard to work with. I thought they were really hard, like, because they are like, if you think lens stuff is hard, then that's even worse, right? And that's how it is. And then I couldn't do all the things I wanted to do, but what I thought was easier to work with was biplate. If you saw that thing, so there's biplate allows you to. It's like if the children are self-similar, as they are in trees, you can even derive the instance you need to use biplate. So you can just derive data, I think. So and that gives you a function, for example, that will update a tree with your chosen function as many times as it can, right? So you can say, okay, like increment all nodes until they reach 5 or whatever, or stuff like that. So I thought that was kind of useful. And then also I've been writing lenses that for example, swap nodes, right? So that's not hard either. I mean, like, you need to use lenses. I don't know how to do it without lenses, right? Because if you have a functional style tree and you descend and you descend and you descend, and then you want to swap within, like, after having matched 5 times on the tree constructor, then you want to swap the children, right? But that's easy because you can make a lens that takes a node and gives you the children as a tuple, and then you have another lens then you have a function that can swap the elements of a tuple. So it's no problem to swap the elements, like in a deep tree or something like that. But it gets more interesting when you want to swap subtrees, right? Because every time I'm swapping a subtree here, I know that the subtrees are the same size. So if I had a dependently typed subtree, then I would have to prove to the compiler that the subtrees were the same height. And that could be pretty hard, no? So maybe not dependently typed. But then the question is, how do I do the translation between my Go code and my Haskell code? Because I would like to like have tests running on every level. But sometimes you reach like at this point where I think that the functional way and the imperative way seem to be so different that this thing, I wonder if it's just inherently imperative, right? But that would be like famous last words. I just think I'm not smart enough to see the functional way to do this. So yeah. So, but the nice thing about the indexes is that they are really, like, for humans it's not so hard to have like an integer index, and then okay, it's supposed to work like this, right? So you see it in a tree, and then it's in context to the tree, and we have symbols to talk about it, right? So what I would want to do in functional programming languages is I would like to have the num instance, right? I would like to have a num instance so that you write some digits, and then you say, okay, this is an index in a tree of this height, and then it says, okay, I know it's on level 5, I know it's this deep into, and I know it has no children or whatever, and yeah. And I cannot see how you would do it without dependent types, because that's such a high ask, right? So I don't know if it's possible. But I like to live with a challenge, right? So that's my challenge. And is there any more? Oh, Joe? Okay, so the question is, can I build it with GADTs and piano? Okay, well, but that's the wrong way, I think, because if you have a GADT, like let's just say ADT. I don't know if we need a G. Well, oh yeah, we need a GADT. Okay, Well, but it would increment, right? Because a piano numeral is only has a successor constructor, so it would increment as you go down the tree. But I want to say it counts down, I think, because I want to. If it just increments, then I would have to have some kind of type equality thing to say when it reaches 5, it shall not increment more. So I still think that's dependent types, no? Because yeah, you're right that I can increment going down, but who builds a tree where the you have an ADT, and what's inside the ADT is not the children but the parent, right? Because that's what you would need then, because you would need to say, okay, and the problem is I want to type the tree by its height at the root. It doesn't make sense to have it the other way around. To like, what would I need to do? Store the leaves and say all of them have the same type because they have so many levels up to a root of this hash or something. I mean, that's how I would need to prove that they are in the same tree. So, yeah, it's like, but I'm sure there's some like theoretical explanation for this correspondence between piano and which way you traverse a tree. And yeah, but to me, I don't know how you don't need dependent types for it. So, but you're right. I tried also with GADTs. I tried it, and I also did stuff like I have a workaround where I'm just building in the Go indexes into my leaf type, and then I can use lenses, index traversals, indexed lens, and all that stuff. So I can work with lens, and I can say, okay, lens knows about my indexes and stuff like that. But the problem is, lens doesn't know what the indexes mean. It doesn't know that when I move them around, they actually become other indexes. So what I can do is I can write some fancy lens that swaps trees, but then the indexes are all wrong, and I have to re-index them. I mean, the trees that you see here in my slides, they are not re-indexed, right? If we look at this one, the indexes are all wrong because I want to show you where they're being moved to. But of course, the indexes are actually just indexes into an array. So in reality, in the Go code, the indexes are not stored anywhere, right? They are just abstract description of what the algorithm would do. It would like, it's like saying, if I say in C, swap the indexes 4 and 5, there's no way to abstractly say that, right? So it's always concrete in C, right? But here it's all abstract. Okay, I don't know if that makes sense, that analogy, but it's like, it's important to understand that the indexes are just a way to think about it, right? Just like if you say in C the second element, you know that is index 1. But it's always a different second element, right? And you can't actually have that abstract notion. So, yeah. Yeah. But I think that's it. Yeah. Thank you. Okay, good.